Welcome back, and in this section of the notes we're just going to be looking at alkanes as fuels. So you're going to need your notes. It would also be helpful if you had the textbook with you, just so you can read the additional material. So we're on page 16 of your notes and we're looking at the alkanes as fuels. And the first thing we're going to be looking at is fractional distillation. So crude oil, which is our starting material, can be separated into different fractions by this fractional distillation. Now the property of the hydrocarbon molecules that allows them to be separated in this way is the fact that they have different boiling points. So it's their boiling point that allows them to be separated. So in come my vaporized crude oil, and as it's being heated, the lighter molecules, the ones with the lower boiling point, will pass up and out, and the ones with lower boiling points will go down and again out. So this is how we can separate the tar from the petrol fractions. There is, however, a problem with this, and this is the fact that the demand for the lighter fractions far outstrips the output from the fractionating column. So we use far more petrol than we do tar. So it makes sense for companies to be able to turn the heavier fractions into lighter fractions, simply because there's just more demand for those lighter fractions. Now the way we do this is called cracking. Cracking is breaking the molecule into shorter ones by heating. Now it does need high temperatures and it's usually done with a catalyst. The reason it needs such high temperatures is you're trying to break a carbon-carbon bond. Now those carbon-carbon bonds are generally speaking very strong, very difficult to break, which is why you need high temperatures and a catalyst. And then you get more of those lighter fractions which are more in demand. So for example, we could crack the large molecule C12H26, which would make 2 molecules of ethene and 1 molecule of a C8H18. So cracked it to form 3 smaller molecules. The other process you need to be aware of is reforming. Alkanes with straight chains burn less efficiently than those of branched or cyclic compounds. So before we can use our alkanes as fuels, quite often they need to be reformed. By reforming, we're going to convert those straight chains into branched and cyclic hydrocarbons. Again, this is done by heating and a platinum catalyst. This reforming process allows the hydrocarbons to burn much more efficiently and reduces something called knocking. It also increases what we call the octane number. So that's why we do reforming. It allows us to burn the fuel more efficiently, reduces knocking, increases the octane number. So for example, I can take my straight chained pentane and I can turn it into cyclopentane. Because I've gone from a straight chain to a cyclic group, I've eliminated a small molecule of hydrogen gas, which is also quite a useful fuel. So crude oil is really important because not only can it be used for a fuel, but also it's valuable as a source for chemicals which are used in the manufacture of a wide range of other materials, for example pharmaceuticals. However, it's also a finite resource, so it's not renewable. Also, because when we burn hydrocarbons, we release a large amount of carbon dioxide, which is a strong greenhouse gas. So this is why we're reserving our stocks of crude oil and looking for alternatives. Cracking, as we said before, is important because we increase the supply of the shorter chained alkanes, which are far more useful. The conditions for cracking, well, we need very high temperatures to break those strong carbon-carbon bonds, and we need a catalyst to enable that to happen at a slightly lower temperature. And we've got an example of that at the bottom of the page, where we're cracking hexane into butane and ethene far more useful molecules. And there's two more examples of this on the next page. Catalytic cracking of decane into 2,3-dimethylpentane and propene, and then reforming hexane into cyclohexane. Do remember, every time you make a cyclic group, you're going to eliminate a molecule of hydrogen, because the change in general formula between an alkane and a cycloalkane. So there's a dire need for alternative fuels other than burning fossil fuels or crude oil. The reason for this is the combustion of these fossil fuels leads to greenhouse gases. Greenhouse gases lead to global warming. Also, if the fuel contains any sulfur, we'll also get acid rain from the sulfur compounds. These are finite resources. So there are three ways that we can reduce our reliance on fossil fuels. Firstly, we can look at alternative energy sources, such as wind, solar, hydroelectric, and so on. We can reduce our energy consumption by improving insulation and improving fuel efficiency, and we can also look at recycling things like plastics, so we don't need to use fossil fuels to make more plastics. The greenhouse effect, you don't need to know this in detail, but you do need to be able to identify greenhouse gases such as carbon dioxide and methane. And they act like a blanket, preventing the solar energy from re-radiating back out into space. CO2 levels are related to climate change in that as we increase the amount of carbon dioxide in our atmosphere, this has several effects. It can melt the glaciers, increasing sea levels. Because warm air can hold more moisture, it leads to more violent storms, leads to sea warming. This also can change the pH of the sea, which leads to things like coral bleaching. You will often see biofuels described as carbon neutral. That's because they take up the CO2 during photosynthesis, which is released back into the atmosphere when they're burnt. However, these are very rarely purely carbon neutral. The processing and transport of the biofuels generally means that more CO2 is released into the atmosphere. Sustainable development basically means not using up these non-renewable or finite resources, and also not producing large amounts of waste, which can be released into the atmosphere. In the next section of the notes, we're going to be looking at the chemical reactions of the alkanes. The first one we're going to be looking at is combustion. Now, alkanes burn in excess oxygen to produce carbon dioxide and water. Now, if you don't have enough oxygen present, you can get incomplete combustion, and that will produce carbon monoxide and or carbon as well as water. You're always going to produce some water, but if there's limited amount of oxygen, you might not get carbon dioxide. So when propane is completely burnt in oxygen, we get carbon dioxide and water. However, it can also be burnt in smaller amounts of oxygen, limited oxygen, and it will produce carbon, carbon dioxide and hydrogen, or carbon dioxide and more carbon. Again, it could burn in limited oxygen to produce carbon monoxide alongside the carbon dioxide and the water. So generally, rule of thumb, the less oxygen we have, the more carbon monoxide or carbon we have. If we really restrict the oxygen, we can get it just to make carbon monoxide and water. So if I burn it in a really limited amount of oxygen, I would get carbon monoxide and I would get water. So both solid carbon, otherwise known as soot, and carbon monoxide are both pollutants. Carbon monoxide is particularly dangerous as it binds irreversibly to the hemoglobin and prevents oxygen being transported around the body. There are other pollutants which are associated with the combustion of alkane fuels, and these come from the impurities in the feedstock. So a lot of the crude oil will contain sulfur, so when we burn the fuels we'll get sulfur dioxide and nitrogen dioxide, as well as any unburnt hydrocarbons. So the sulfur dioxide, which happens when I burn the sulfur in oxygen, can react with more oxygen to form sulfur trioxide. The sulfur itself can burn with oxygen to produce more sulfur dioxide. The sulfur dioxide and the sulfur trioxide can then react with water to produce acid rain, and that's why a lot of time and money is spent desulfurizing the fuel and feedstocks during a desulfurization process. Now nitrogen, as you're well aware, is a very unreactive gas. However, the high temperatures in the engine can cause atmospheric nitrogen to react with oxygen to produce oxides. Those oxides can then react with water to make acids, and this contributes again to acid rain. Most cars are now fitted with what we call catalytic converters, and these catalytically remove some of the pollutants from the exhaust fumes, and this does things in 3 ways. So firstly, it can convert carbon monoxide into carbon dioxide. Carbon dioxide is still a very powerful greenhouse gas, but it's not as toxic as carbon monoxide. It can oxidize unburnt hydrocarbons. So some hydrocarbons are not burnt in the engine, so we need a way again of getting rid of those hydrocarbons. Lastly, it can react nitrogen oxide and carbon monoxide to produce nitrogen and carbon dioxide. Again, slightly less dangerous and less toxic than the oxides of nitrogen and carbon monoxide. The one pollutant you can't remove via this method is sulfur, and that is why most sulfur pollutants are removed before the fuel is burnt, and that's a hydrodesulfurization reaction. As well as designing vehicles which use or burn less fossil fuels, one alternative is to keep the cars we have but to change the fuel that we use to drive them. The 2 biofuels we need to be aware of are biodiesel and bioalcohols. Biodiesel is produced from vegetable oils, and bioalcohols are produced by the fermentation of sugar. We should also be aware that many vehicles nowadays are being designed as electric vehicles which run on batteries, and we're going to be studying battery technology when we look at redox in the upper 6th. So there are many factors we need to consider when comparing biofuels to each other, as well as comparing them to conventional fuels like petrol and diesel. And in fact, when we're comparing the use of biofuels for transportation versus electrical vehicles. So one of the first things to think about is land use. So these are all grown from plants. Would it be better to use this land to grow food or fuel? Secondly, yield. How quickly the plants grow, how much of it is wasted, how easy it is to convert the plant into a fuel. All of these questions need to be addressed. Manufacture and transport. How much energy does it cost or does it take to process the fuel, transport it, and grow it? And last but not least, how close is it to carbon neutrality, to being carbon neutral? No biofuel is completely carbon neutral due to processing and transport costs, but it's closer to carbon neutrality than something like petrol or diesel. So that finishes this section of the notes, just looking at alkanes as fuels. If air pollution is something that interests you, there's a very good book called Cleaning the Air by Tim Smedley. It's on our reading list, so do check it out if you have an interest in air pollution and how we can combat it. So until next time, stay safe, keep well. Bye bye.